Our speaker this week is Milo Buitrago-Casas, who is a postdoc at the Space Sciences Lab at UC Berkeley. He got his PhD in physics at Berkeley earlier this year. During his doctoral studies, Milo investigated X-rays from the quiet sun using observations obtained with the NASA sounding rocket payload. He's now working on developing cutting-edge instruments for space high-energy observations. He's also implementing machine learning techniques to predict the largest explosive events on our sun. So I'll leave it to Milo.
Thank you. Thank you for the invite, and thank you all for coming. I'm just gonna remove the mask during the talk so I can project my voice better. So I'm happy, I'm very excited to be here today. I spent a few years here as a student, and I was always there, and this is my first time standing here. So if you are excited, I'm probably 10 times more excited. So what I want to share today is the passion several people working here and in the entire US and in the entire world, the passion that we have to live and study and understand our star. Which star? Not this kind of stars, but a star which is way more interesting than living with any of these or any other rock or pop star. Is this star. It's our star, the sun. This is a sequence of images, real images. This is not an animation, this is not a sci-fi movie. It's a sequence of images in extreme ultraviolet of our sun just a couple of months before. Living with a star, living with next very close to this star, it's very, very interesting, and it's vital. It's the foundation of our life being here. We, all of us, humanity, every human being, every being in our planet depends on the sun, the existence of the sun, and the perfect configuration that our planet has along or traveling around this star. Several of us, as I said, we dedicate our lives to look at the sun. Of course, we look carefully at the sun using these eclipse glasses that you can find in the Astro department, you can buy online. And I encourage you to buy those kind of glasses because there is a nanular solar eclipse coming next year, and there is a total solar eclipse that is going to cross the entire US in 2 years. So better you rush up, get your eclipse glasses soon, and look at the sun. Careful. Why to study the sun? We study the sun because it's our fuel. Every time you turn on your TV, every time you use your car, it doesn't matter if it is electric or if you use gas or any other fuel, you are using solar energy. Every single piece of energy that we use here in the planet comes from the sun. And when I'm saying this, is the gasoline that you use for your car, for example, we are changing to use more electric cars. But that gasoline comes from petroleum, and you guys know that the petroleum is just the product of dinosaurs and plants and beings that lived on our planet a long, long time ago. So it's just important to us being here in the planet because it's our fuel, but also because it is a source of inspiration. This is a picture I took, but I know like any of you guys have took even better pictures than this during a sunset that you probably saw coming here because this is just starting a couple of minutes after the sunset. So it's not only a source of inspiration, but for everybody and us as astronomers and astrophysicists. But for us studying the sun, we enjoy the sun not only the sunsets, but we enjoy trying to understand the physics, trying to understand the phenomena that happens at the sun. Why to study the sun if you have plenty of stars? I'm sorry, this doesn't look much okay, but this is a picture I took from the Chabot Observatory in the mountains of Auckland. If you guys haven't gone there and visit, please do. It's free, it's fully free for everybody every Friday and Saturday night. And they have the biggest telescopes around here, open to the public. And several nights I went there, and one night there is a dome. Imagine there is a dome, but we live in, there is a dome on this corner. And you can still see a few dots in the image, very tiny dots. Every one of these dots in this image is a star. And you need powerful telescopes, like the ones in Chabot, the one that is on top of the roof here in the astro department, because you need to collect as much light as you can with a large telescope to be able to see tiny, tiny details of the star. And even so, you can't see much. If you study the sun, I'm trying to convince people to study the sun, it's like if you took one of these stars, whatever star you see at night, but you really bring it very close to us. So it's like when you have a camera, but instead of taking a picture of an object that is miles and miles away, it's just a few centimeters from you. So the amount of detail that you can see is humongous. And I bring these images because these are the highest resolution images today in UV of the sun. These images were taken with a sounding rocket. That's a sounding rocket similar to the one that we have launched in collaboration with the Space Science Lab here in Berkeley, but this was launched by people in NASA Marshall in Huntsville, Alabama. And this, right now, you are seeing the highest resolution image of the sun in UV. It's night, I know, it's night, and anybody naively can say, well, you cannot see the sun at night. That's a lie. Because you all are seeing the sun, not right now, but like a couple of minutes ago when I was finishing my slides. This is how the sun looks right now. And if you go and Google the Solar Dynamic Observatory, you will be able to see the sun right now. Why? Because yes, we are on a planet, but we now dominate satellites. We dominate space. We can go up to space. We can launch things to space, and we, in particular, can launch telescopes to observe the sun. And this is the sun how it looks right now. Yes, it's a ball. You can recognize that it's not an homogeneous ball, but it has some features, some black features. Those spots are called sunspots, and we'll get to talk about sunspots in a while. This image was taken with this satellite, the Solar Dynamic Observatory, which was launched and put in orbit in February 2010, if I'm not wrong, 10 or 11, one of those 2 years. And it's been observing the sun since then, and it's still working. And yes, it observes the sun's invisible light. That's how you would see the sun as if you put the eclipse glasses that I showed you in the first slides. But it doesn't have a single telescope. You can see 4 telescopes on top. Each of those telescopes is able to observe the sun in extreme ultraviolet. And if you see the sun now, not in visible light, but in extreme ultraviolet, it looks way more interesting. So the image 2 slides ago and this image are taken at the same time, but you can see now that you can start seeing different phenomena, different physics at the sun if you look with different eyes. This is 12 years of the Solar Dynamic Observatory. The picture in the slide before, it was the sun now. But the team, the Solar Dynamic Observatory team, they made this image overlapping several images taken like 1 week apart during the whole 12 years of observations, and this is the result. Now you start seeing some very interesting stuff here. Like for example, you see that the brightest part of the sun are very close to the belly of the sun. and the sun is kind of bald in both poles. Like, that's interesting, and that's already telling us something about the behavior of this star. This is one filter in extreme ultraviolet, but it's not the only filter we can use to observe the sun. This is also the sun right now. If you go to the and look for Solar Dynamic Observatory, you'll see images, invisible light. You can recognize that kind of boring yellow ball on your left up corner. But then you can see all the different filters in extreme ultraviolet here. This is kind of violet, kind of gray to white light. And this is what we call soft X-rays, and these on the bottom are really interesting, because although they look boring, they are gray, black, and white. But the one on your left is the magnetic field. We are able from here, from Earth, from space, but that spacecraft is just a few hundreds of kilometers away from us. We are able to measure the magnetic field on the sun. What is a magnetic field? Is magnets. It's basically the same phenomena that makes your magnets to hold on your refrigerator. And then you see, this in the middle is kind of boring also. It's just visible light. But the one on the right, it is showing you the movement of the solar surface, and we'll get to talk about that movement, because we can learn a ton from that movement. We call these Dopplerograms because we are basically measuring the Doppler effect, and you guys have heard of the Doppler effect if you have seen the Big Bang Theory, and when Sheldon was in Halloween, he explained very well what the Doppler effect is. So this is the sun now, and this is how the sun has looked in the last 24 hours. I made this movie for you guys. So on the background, you see the extreme ultraviolet, a sequence of images of the sun, and on top of it is an extrapolation of what we believe with some models. It's the three-dimensional geometry of the magnetic field. So the magnetic field that you saw in the slide before that we measure, we are measuring that down at what we call the solar surface. And with some models, we extrapolate these lines. So this is a unique way we are starting to see the sun very recently. This is happening just a few years, mostly a couple of decades, no more than that. So we are living a golden age to observe the sun. Why? Because yes, this is how you see the sun from Earth, basically. But you can get closer. And we said, if you get closer, you could see way more details. And this is also very new. This is brand new. We are so happy with these images. What you are seeing here, you will see, well, this looks similar to what we observed before. The difference is these images were taken with a spacecraft, which is called the Solar Orbiter, which is traveling very close to the sun in an very elliptical orbit. And these images were taken just 77 million kilometers away from the sun. Just remember that the distance between the sun and the Earth is more or less 150 million. So this is halfway, basically, between the sun and the Earth.
Still ultraviolet?
It's still ultraviolet, same wavelength as the one before. But then you can start seeing some small, very tiny brightenings, like campfires. And in fact, solar scientists start calling these campfires. Some people are happy about that name, some other, I love to see those arguments. And just so you get an idea of how big are these campfires, this is the size of the Earth compared to one of these small fish. So this is something new that we are starting to see thanks to this spacecraft, the Solar Orbiter, which is a collaboration between NASA and ESA, and which was launched in February 2020, that's when all this apocalypse was starting. This was launched using this vehicle, I don't know, you get to see a couple of launches. It was, I remember I was in Goddard at that time, and we had the opportunity to travel and see the launch, but the pandemic was starting, and in the end they didn't take it, so I saw this also like, okay. But I got to see some rocket launches. I'm gonna show you in a second. One of the very cool things that this spacecraft, Solar Orbiter, is gonna do is, yes, get very close to the sun. How close? It's 60 solar radii. So just so you get an idea, between the sun and the Earth, that distance is like if you put 110 suns, one next to the other in a line, and in the end, after 110 suns, it would be Earth. This spacecraft is gonna get to 60 solar radii, so 30 suns, that close to the sun. But that's not the only goal of this spacecraft. This spacecraft is gonna also get into an orbit which goes outside what we call, which is a weird word, the ecliptic. The ecliptic is not other thing but the plane that the Earth generates in its travel around the sun during a year. So that movement, the Earth or orbiting the sun, is described in a plane. This spacecraft comes out of that plane in an orbit that is like, sometimes, I'm exaggerating this movement because I think the inclination is only 20 something degrees, but like you can imagine something like this. And what is cool about it is that for the first time, we are being able to see the solar poles. And this is the first image of that spacecraft, taken by that spacecraft, of the south solar pole in one of its closest approach to the sun. This is new. This was released to the public like a month ago. So I'm bringing you news. That's what you're gonna see today. And this is just to show the orbit. I should have put this before. that shows the lights doesn't help. They don't help much, but you see the sun in the center. You see a few planets there. I think it's Venus and the Earth, and the white orbit is the orbit of the solar orbiter. And you see that it's very elliptical, very eccentric, meaning it's a stretch. And you see that that spacecraft is not all the time very close to the sun, but it gets close to the sun and then it gets away. And the dates over here on your right are the gravitational assistance. So to control the orbit and to get those spacecraft in these very weird orbits, engineers get helped by the gravitational force of the different planets to deflect the orbits of this spacecraft. This is one example. I'm going to show you another example. But another cool thing of having a spacecraft traveling very close to the sun is that, yes, one thing that you can do is like, okay, now I'm even closer, right? So I can take pictures closer and see details. That's one thing, okay. But the other thing is you can go there with a I'm excited. This is an analogy, it's not that you literally go there, but you can put a multimeter or anything, an instrument. And because it's very close, you can measure different physical parameters very close to the sun. And that is one of the things that this spacecraft, and another one I'm going to show you in a couple of minutes, are doing. That kind of measurements are called in situ measurements. You are measuring inside that ambient. And I love this diagram because it's showing the orbit solar orbiter, yes. But you see the intensity, it changes. And that intensity is measuring the amount of solar energetic particles. So the name tells you what they are measuring.
Sorry, this may be a dumb question, but the highly elliptical orbit, is that just because it can't stand being too close to the sun for any length of time, or is it just because of the speed that would be required to maintain a closer orbit?
It's a couple of two things. So the question is why the orbit is so elliptical, so eccentric, so stretched. It's a combination of one, the spacecraft not being able to stand that hot temperature. So you can imagine, we're going to talk about that once you get closer and closer to the sun, it gets hot and hotter and hotter. So it actually gets hot, but then once it gets away, it gets fresh again and relaxed. I'm imagine that. So that's one argument, and the other argument is because it's really hard to go to the sun. The Earth right now, everybody here in this room, we are traveling at a speed of 30 kilometers per second. So between these two sounds, we move 30 kilometers in a direction that I don't know, because that depends like where the Earth is facing, and I don't know where north is. I think it's like, okay, that way. I don't remember. So we are traveling at a really high speed. So someone one time suggested one solution for all the trash that we generate is why we just don't put all the trash in a container and ship it to the sun. Well, it's really hard because you need to put engines to counter that high speed, and then assume that you can do that. Once it's at a speed zero, then it's gonna do a free fall into the sun, right? So it's kind of similar. It's not that extreme, but the very eccentric orbit, it's an intermediate step between like traveling in a very circular orbit. I know our orbit, the Earth orbit, is elliptical, but it's very round. It's very round. The eccentricity is tiny. So it's basically going from that round orbit to a free fall. So that's a good question. Here we start seeing that at different times in the orbit, you see more or less very energetic particles that come from the sun. That's not the only thing we see. We have seen also invisible light, the sun with the highest ever resolution, and that's also news. This is happening now in the last couple of years. This is an image of what we call the solar surface. Although I need to explain, I'm going to explain in a little bit that the sun doesn't have a solid surface like this table. It's just a layer that we call a surface because I'm going to say historical reasons. But the cool thing up here is that you start seeing bubbles, granulation, similar bubbles as the bubbles that you see when you are boiling water. It's similar, and in fact, the physical process is very close. The cool part is that we just recently got the resolution enough to see pieces of the solar surface that are the size of a common city. You can imagine the size of San Francisco. You can see that. And you can see more romantic and beautiful stuff. I'm also going to show you several images that kind of intersect science and art. This is a art. And you can save this and find it and send it to you in the option. I forgot the name. The name of that day in February 14th. Some Valentine's Day. This was taken with this telescope, which is the largest ever telescope dedicated to observe the sun on the ground. So this telescope is in Hawaii. It's in an island in Maui, and the other astronomers in other fields they always made fun of us who study the sun because we use very small telescopes. And the reason we use small telescopes, and try carefully this, if you use a lens, any lens during a sunny day, you can burn paper. So imagine the bigger is your telescope, well, you start like facing really hard challenges to don't burn your detectors. But we managed finally to use a 4-meter diameter mirror, and in fact, more news. 3 weeks ago, we were in Maui with other solar scientists, and I got to take this picture. So this is the mirror that we are using, and you can see the size of a common person there. It was explaining how they construct all this facility, and you can see on top of him the mirror. The mirror is standing sideways. That's its resting position. But it's a beautiful place. Plus, like it's on top of a mountain in Hawaii. If you ever get to go, they have some visitors staff around there, so please go and visit. It's a really cool place to be. So, conclusion so far, we are seeing the sun as never we have seen it in history. This is one of my favorite images of a total solar eclipse. Please go and get some of these eclipse glasses, but even if you cannot find them in April, I know it's early April, I'm sorry I don't remember the exact date, April 2024, put that in your calendar, because that is the total solar eclipse that is going to cross the entire US, and you won't need eclipse glasses during the totality. Just during the totality, that is like a couple of tens of seconds, a minute. So literally, if you look at the sun at that time during totality, you will see this with your naked eye. You will see something like this, and these two pictures were taken during the eclipses in that happened in Argentina a couple of years in 2019, Argentina and Chile. So again, since we don't need to even go with a very crazy high-tech spacecraft, we have in our hands really high-tech cameras, and these days from the ground we can take pictures of the sun as never before. We have been observing the sun with this kind of technology for a few decades already. I like this image because this summarizes observations from Soho, which was launched in 1996. I don't forget the I don't remember the month. And the cool thing is this team made this infogram. I also love this infogram, putting one image of the sun at the same day of the year during all these years, the 25 years that happened until 2020. I suppose, yeah, this is 2 years old. But then you see something strange. The sun looks different every year, and in fact, it seems that it has a cycle. Because in 1996, it was very quiet. But by 2000, 2001, 2, it's very active. Right? And then like by 2007, it's still again quiet. But it gets active again, like around 2014, 2015, and now it's quiet again. It's a cycle. It's the solar cycle. And we have observed that solar cycle for several decades. I love this infogram. This is, it's Laura Hayes. These are flares. I'm going to talk about flares, eruptions that happen on the sun. And this, on top, we are plotting time on the horizontal axis, and on the left, on the vertical axis, we plot the latitude, the solar latitude, and you see something. That diagram on the top, it looks like a butterfly. So again, another intersection of art and science. And in fact, we call it the butterfly diagram, and if we count the number of active regions during the last decades, we see how those butterflies have a periodicity. And that periodicity in number of active regions on the solar disk is about 11 years. We have studied this butterfly diagram, not only counting sunspots, that you already saw some sunspots in the images, but we have studied that measuring also the magnetic field. You remember the magnetic field image, boring image that I showed you a few slides ago? Well, if you use that kind of images and you plot the magnetic field along some time, you can see some butterflies here as well. We find that the periodicity in the magnetic field is not 11 years, but twice that value, so 22 years. The actual cycle of the sun is 22 years. And why it happens, why there is a magnetic field? Well, we believe that in the interior of the sun, the intersection layer that we call it tachocline. At the tachocline, the global magnetic field of the sun is formed, and then because the sun doesn't rotate as a solid body, the sun rotates faster close to its belly and it's lower at the poles, then that movement of rotating faster at its belly, it's entangling the magnetic field, and that entanglement makes the magnetic flux to come close to the sun's belly instead of close to the poles. And that's how we believe that we can explain partially the fact that we see more bright parts on the sun close to its belly, as we have seen, and also we believe we can explain partially the fact that we can see the butterfly diagram. How we can study the solar interior? Have we sent any spacecraft, anybody, to measure the inside of the sun? Well, no. I'm going to explain in a little bit how we study the interior. But here I'm just going to mention that we believe that the solar interior is divided in 3 big zones. So the first zone, the more interior zone, the core of the sun, we call it the core. And that's where we believe, again, according to models, that the 99% of the energy that is emitted from the sun is actually converted there in useful energy by nuclear processes. Then the second region is the radioactive region, and we call it that way because the processes, the energy gets transferred from the interior, from the interior outside, is dominated by radiation. And then the last zone is the convection zone, which we call it that way because there is where you can see convective cells, convective bubbles emerging from the solar interior. How we study that? Well, we haven't been able to send anything there, but that's where the bigger boring image that we saw at the beginning comes into action. So we measure the Doppler effect. How? Well, it's like you can imagine. Let me go back and forth because I love art. Can I do this? Yes. So you can imagine that the solar surface is like a bunch of speakers all singing at once, and by measuring the difference between the different speakers, you can infer how the solar interior is. Something similar to this phenomena. Oh, this should start. Yeah. Similar to when a musician, I'm not a musician, but I wish I was a musician, hits this kind of plate, And it's awesome to see how the surface wave travels on that surface. And by studying the movement of that surface, you can infer the physical properties of that object. So in a similar fashion, studying here we are super exaggerating the movement of the sun, but studying that movement, you can infer how the sun is inside. So that's how we are able to sample, to study the solar interior. The sun doesn't stop at what we call the solar surface, and here is probably a good moment to define what the solar surface is. So the sun is kind of an onion, where you have the core, you have this is not the actual interior. It's the core, the radiative sun, the convective sun, and then it comes to the photosphere. The photosphere is the other name that the solar surface receives, and is that layer from the sun where the visible light, the same kind of light that our eyes can see, can emerge from the sun without stopping. That's the solar surface, but it's not a solid surface. It's a layer. And then it comes something that we call the chromosphere and the corona. Why the corona? Because that's the part of the sun that during a solar eclipse you can see as a corona, right? So, but that corona is very weird, and it's not the corona that we know is very weird. It's another corona, it's the solar corona. So if we go back for a second and we start looking at the solar interior, and we go, imagine that we can go with a thermometer there and measure the temperature inside the sun, right at the core. Well, we get a measurement. We believe that temperature is about 15 million degrees. At those high temperatures, it doesn't matter if it is Kelvin, Celsius, Fahrenheit, very, very hot, right? And then our experience, and we don't need to know thermodynamics to know that if we start getting away from the sun and measure the temperature should be a little lower, and lower. Okay, that's expected. If I move away, the temperature should drop, and drop. And that's true until you get at the photosphere, the surface. But once you pass the photosphere and you get to the corona, to the solar corona, and you measure the temperature, and we have measured that temperature in so many ways, and we always get the same result. The temperature is higher at the corona than inside at the photosphere. And we don't know why. We don't have anything. In fact, let's see if this works.
I know.
It doesn't
This
sound.
perpetual motion that you made today
I don't
is a
have
joke.
volume
Just keep
here.
going faster.
But
and
basically, if
faster.
you go and look
Please,
to
get
this
in here.
episode of
In this
The
house, we
Simpsons,
obey the laws
you'll
of
get to see
thermodynamics.
that Homer gets really mad at Lisa because she's breaking the laws of thermodynamics. And this is basically what we are mad at the sun right now, because it seems that the sun is breaking the rules of thermodynamics. This is the only plot I'm gonna show, like a sentence plot. This is temperature, and this is altitude above the solar surface. And what you see is that at the solar surface, the minimum temperature can be between 5 and 6,000 of degrees. But then when you move away, it's not a small increase, it's a dramatic increase. It goes up to several, this plot is not showing that, but it goes up to several million degrees. It passes from 5 to 6,000 to tens of millions of degrees, and we don't know exactly why. In fact, if you go to Wikipedia and look for the list of unsolved problems in physics, you'll find the corona problem. We don't know, and we need your help. We want you guys to join the scientific community. Although I lie a little bit, because it's not that we don't have clues, we have hypotheses. This is the cool scientific method. You know, like you identify a problem, you don't know when you try to imagine, like, okay, how we could explain this. There are a few hypotheses. My favorite, it doesn't mean that it's right, it can be wrong, is that there is plenty of small solar eruptions happening all the time in the solar corona. And those eruptions, as you know, when there is an eruption, an explosion, there is always a release of energy. Yes, here on Earth, you get a big sound, a big bang, you know. But you also get other kind of energy releases. And if you get an energy release, you can get an increase in the temperature. Explosions are hot. Nobody wants to go and touch whatever explodes just a couple of seconds ago. So if you imagine that there is not one or two, but a ton of small eruptions happening all the time at the sun, then you could explain the corona. If those small explosions happen, you would expect to see X-ray emission. Those explosions are so energetic, the physical parameters are right enough that you would need to see those X-rays. Have we seen those X-rays? No yet. Why not? They are very faint. Because they are very faint, you need really, really sensitive instruments to observe them. And here at Berkeley, at the Space Science Lab where we work with a multidisciplinary team, NASA and other universities, to put together what we call FOXY. I love this name. It's the Focusing Optics X-ray Solar Imager, and is an instrument, it's a telescope that has flown as the payload of a sounding rocket payload from NASA a few times, and which goal is to observe the sun in X-rays with a very sensitive technique. How come? Well, we use mirrors. How difficult is to use mirrors to focus X-rays? Let me explain. Let's first consider visible light. So you have a mirror, a standard mirror, and you have a ray of visible light coming to the mirror, and it's easy to know that that ray is going to get reflected. And that's what all my colleagues in other fields of astronomy, they do with their big telescopes. Well, for X-rays, the problem is, if you have the same mirror, and there is an X-ray coming to that mirror is not going to get reflected that easy. If that ray comes in that direction, it would get not reflected, but transmitted. How you can get that ray to get reflected? Well, two things. One, you need to work with very heavy mirrors, and two, you need to polish that mirror really, really well. And three, you need very small incidence angles for the X-rays, and then you get a reflection. So if you do that, if you have one mirror, why you don't use two mirrors? So that's what we use. We use an X-ray coming here, it hits the first mirror, it hits then the second mirror, and then we focus that X-rays. But why do you use two mirrors when you can use four mirrors and repeat the same technique? And then now you have two X-rays coming to the same spot. Why do you use four mirrors when you can use a bunch of mirrors all nested together and focus all those X-rays into a single point? That's exactly what we did. So imagine that the X-rays come from this bluish, X-rich sun over here. So it has a bunch of X-rays, and we use one of those optics all nested together here, and that optics focus all the X-rays into a point down here where we put a high technology detector able to detect those X-rays, and that's what we put in the rocket. But why do you use only one optics and one detector when you can use 7 of them? So this is what we did, and we put 7 of these telescopes able to observe the sun in X-rays in a NASA sounding rocket, and we got to launch that rocket, and that I was able to go to that. And in fact, I was able to turn on the high voltage of my detectors, and I was so happy to see the sun in X-rays. So this is what we are testing. These are suborbital flights. They go to space only for 15 minutes, and then they return to Earth. It has flown successfully 3 times. We got funded for flying a 4th time. We have flown this from the White Sands Missile Range in New Mexico, and in a year and a half, almost 2 years, we're gonna fly from Alaska. And this is the good news. This is also, I told you, like, I'm bringing you like hot news here today. And one of the goals of Foxy 4, the 4th time that we are gonna fly, is to fly at the same time the other spacecraft. So I told you about solar orbiter, right? The solar orbiter is the one that gets very close to the sun. 60 solar radii, right? That's the closest approach. Well, that's not the only one. There is another one called the Parker Solar Probe, which we are very proud of. Is this huge machine over here? It's been flying around this. Well, it was launched in August 11, I think, or August 12, 2018. And I remember that day because I also got my ticket to go and see the launch. And then because I was working with Foxy, I was not able to go. But this is the other spacecraft that is traveling very close to the sun. It's the size of a common car. And you can see the spacecraft over here, some engineers just before the launch. And you can see my PhD supervisor, Professor Stuart Hale, who was the principal investigator of one of the instruments that was launched in that spacecraft. And here he is giving a talk at the Space Science Lab and showing the instrument that now is orbiting the sun. It's not exactly that. This was the spare that we had in case the one that is actually traveling failed. Fortunately, it never failed. So now Stuart has this to show to the general public. Hopefully, we can invite him here to talk to you next. And because we love rocket launches, this is the Delta 4 Heavy that we use to launch the Parker Solar Probe very close to the sun. This is the spacecraft ever made by humankind, closest to the sun already, and the fastest ever machine ever made by the humans. And this spacecraft has a weird name, because, okay, the one before is Solar Orbiter, and this is the Parker Solar Probe. Solar Probe, yes, we all can understand, but why Parker? Well, Parker, because of this scientist, Eugene Parker. He unfortunately just passed away a couple of months ago. But Eugene in the 50s, this is a picture of Eugene in the 50s, he got to propose crazy ideas at the time to explain how the sun works. There are plenty of very interesting stories about how these young scientists suffered to publish out-of-the-box ideas, out of the box for the rest of the scientific community. But in the end, he was right. And it's important because this is also, again, he was the first ever scientist to have a spacecraft named after him that was still alive to see the launch. There is no other scientist that enjoyed of that privilege. And this is Parker Solar Probe right now. I literally also took, I made this slide before coming here, and you can go and see the approaches here. This is fantastic. This is also an elliptic orbit, but Solar Orbiter, the other spacecraft, can get as close as 60 solar radii. The Parker Solar Probe is gonna get down to 9 solar radii. And in fact, today it's getting into the approach number 13 to the sun. And in September the 6th, that's in 5 days from now, it's gonna get to the closest approach, again, ever made by any human-made spacecraft. It's gonna get to 11 solar radii on September the 6th. We all are very excited, and here you can see the current speed, distance to the sun, etc., etc. This is a really good time to track down these numbers. If you go to that website for the next couple of days, because you'll see those numbers change so fast, day by day. It's so cool. The Parker Solar Probe already found very novel phenomena. One of them is what Stewart and others call the switchbacks, literally these magnetic switchbacks. So they are reverse magnetic fields that we as a team were still investigating. We don't know the physics, the exact physics of them, but they may be related even with the coronal heating problem. Who knows? Yeah, this is another plot because if you are interested in going into the details of this kind of observations, Stewart just submitted to Nature, one of the most prestigious journal, a paper summarizing their findings. I'm gonna try to explain and try to make fair the explanation here of what he's finding is that these switchbacks come, the nature come down from the solar surface, where those bubbles, big bubbles that we saw a few pictures ago, basically generate these switchbacks that travel all the way up into the interplanetary space.
You went from Foxy to this probe.
Yes.
I lost out on your hypothesis about X-rays. Did you find, or have you, in those first few launches, seen any evidence yet?
We don't have enough. So the question is, I'm gonna mention a few things about that in a second. But the question is if we find out any signature of X-rays with the sounding rocket. The answer is we found a proxy. But since we had only 15 minutes of flight, 6 minutes of observations, is not enough time to get a certain answer. So in fact, we have proposed several times already to NASA to fund us for a permanent spacecraft using that technology. So we get more time, not minutes, but days, months, years. And we have paused into phase A and B, which means like exploring the technology and the feasibility, but no success so far. So yeah. But anyways, I'm showing this, and I switched to the Parker because in 2024 we haven't decided totally yet if we are going to fly in April or in September, but we expect to fly from the Parker flat in Alaska. It's going to be the first ever also sounding rocket flight to observe a flare, a solar flare, a big eruption. And we are going to fly together with another rocket. In fact, we are Foxy here, and High Seas over here. High Seas, the other sounding rocket that I showed the product of in the first slide, when I showed you this is the best high-resolution image that we have in UV so far, that was taken with that other rocket. So we are going to fly at the same time. Why? And at the same time as one of the closest approach of the Parker Solar Probe, PSP, Parker Solar Probe. Why? Because our intention is to observe a solar flare and with the rockets remotely from Earth, observe what's happening down on the sun here. Knowing if there are X-rays, how is the UV emission, blah, 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 infer the physics of that. And at the same time, having PSP up there, but very close, measuring in situ, measuring in there, the physical properties of the sun. So with these two, we expect to get more clues on the physics of explosions at the sun and with that, maybe some clues about the open questions that we have from our star. Not everything is rocket science, and finally, my rocket, I love it. That's the reason I couldn't go to the other rocket launch. Yes, it's smaller, but because it's small, you get to play with it a lot. And we could put a few GoPro cameras, the same GoPro cameras that you could use every time you go biking. Here's a close up of that camera. And this is the footage of those. It's very fast. It's not slow at all. And here are the two GoPro cameras. And this. We don't have people inside, so we don't care that the rocket is spinning. So you see, as it goes up, it's spinning, spinning, spinning. You get to see the clouds. You get to see the sun right there. More clouds over there. I think there is a moment in which you can see the nose cone of the rocket. Let's see if we can see it. Oh, there is an opening. Oh, you see the nose cone here? That was so cool. We were super lucky. We got really beautiful footage. And once we get into space, we observe the sun. So this big ball over here is the sun, invisible light. Because we had also a telescope, invisible light. These are the X-rays. Every single dot in this movie is an X-ray. And yes, it's difficult to see, but we're not seeing the whole sun. We are seeing a portion of it, but you can see that we can identify an active region over there. And then after we had those 6 minutes of exciting observations, the payload comes back to Earth, and there is a parachute that gets open, and we landed on the White Sands Desert. And you see, we were super lucky. You look at that shadow. And then, this is the cool stuff. We get to collaborate with the Navy and the militaries, and that's what we should use science for is to use helicopters instead of going to war, and we rescue your payload. So cool. And a couple of engineers and other scientists, we came out with hey, he's a payload. And just to finish, because I think I passed the time, let me just finish saying how the sun, how to live with that star, and how that affects us. We are a society today that strongly depends on satellite communications. And the fact that we live very close to a star that sneezes from time to time, and every time it sneezes, it can be so dramatic as this. This is not data. This is clearly sci-fi. But yes, it can attack one of our satellites. It can attack our grids, electric grids, and oh my God, this a power outage. So it's not as dramatic as that, but something like that may happen. So here, this is data. So the green is the sun in UV. The blue around it is an artificial eclipse. So we cover the sun, which is so bright, and then we get to see the corona. And you see that from time to time, there is a big explosion that is ejecting solar hot material into the interplanetary space. And that material, from time to time, can get to a planet, it can get to Jupiter, Saturn, it can get to Earth. Sometimes, this is not data, this is also an animation. So, yeah, sometimes a big chunk of solar material can get to the Earth and then interact with our planet. Fortunately, we are in a paradox, because the Earth has this magnetic field that is our shield for that hot material. And in fact, every time there is a solar storm, that's called a solar storm, we can see this beautiful, beautiful phenomenon. I wanted to see two phenomena in life before I died. One, a total solar eclipse that I did already twice, I'm not gonna say it. in 2024, and 2, I want to see auroras. I haven't been able to see this because 2 things need to happen. 2, having good weather and bad weather. You need good weather here on Earth, so you have a clear sky, but you need bad weather. You need a storm in space, so you get energetic particles to see these kind of things. If it is good to see an aurora from Earth, imagine how it is to look at an aurora from the International Space Station. It's beautiful. It's gorgeous. I told you, like the intersection between science and art. This is insane. This is a paradise. And if it is beautiful to see an aurora from space, imagine how it would be to see an aurora in another world, in another planet. Well, you don't need to imagine. It was released this week. The James Webb Space Telescope released this image of Jupiter with a beautiful couple of auroras on its poles. Really, really beautiful. So, yes, it's true, we can get beautiful landscapes when there is a solar storm. But it is true, I was saying, that we are a society that depends heavily on satellites. So heavy, this is old. This is like already 10 years old, this animation. We have several tens of thousands of satellites. Now, with the SpaceX and all these private companies coming our skies with more and more satellites, this is even worse. And the satellites out there, they are not fully protected. And the reason is, although the Earth has a magnetic field, you saw that shield is not homogeneous. That shield has a hole. And this map, you can recognize the whole world here. Every point in here is a satellite damage across during a year. I don't remember which year. And you see that it looks like bees over here. It was honey here, right, over South America. That is called the South American magnetic anomaly, South Atlantic magnetic anomaly, sorry. And it is a hole, it's not fully a hole, it's not something we have done, it's nature, that's the nature of it. It's a slightly less intense the magnetic field there. So the satellites are more exposed to the hazards, the space hazards, and they can get damaged every time they cross that place. In fact, here at the Space Science Lab in Berkeley, we control several satellites as a rule of thumb. Every time a satellite that we control passes that anomaly, we turn the satellite off, and we turn it on again once it crosses that anomaly. And this is based on yeah, this is not working. But I'm sorry, it's not working. Oh yeah, this is based on models. It's partially data-driven models. You see, the anomaly is the blue. The blue is where the magnetic field is less intense. So you see that it's covering the whole South American region and South America. This is, and in fact, it has all kind of connections. Like it seems that probably it has some connections with the amount of skin cancer that happened in Uruguay. There were some studies 4 years ago, still like a topic of interest. And these are some of the effects that can happen. They happen more often if you have more and more flares. We found that the sun doesn't have the same amount of flares and activity all the time, but it has cycles, remember? And we said that those cycles are in cycles of 11 years, and we just are exiting at the exit of a minimum, and we are racing to a maximum of those cycles. So in the next couple of years, we expect more and more and more of those solar flares. We have seen those solar flares happen all the time. They have happened at the sun for millennia. But this is the first time we are so susceptible as a technological advanced society. We depend on satellites, and this can be a problem. And that's why, apart from studying the sun as a unique scientific interest, but there is a practical, very practical interest here. With this, in conclusion, we live a golden age to study the sun. Several spacecrafts looking from Earth very close to the sun, like the Solar Orbiter, the Parker Solar Probe, sounding rockets that we are launching in coordination with NASA here at the Space Science Lab, CubeSats also that we expect to launch, and you didn't get the opportunity to talk about this CubeSat. Is called PADE because it's very PADE, and the biggest ever telescope to observe the sun that is in Hawaii. Come join us. We need everybody, the young generation especially. And if you are here and if you are interested in any of these topics, please visit, please visit our website, the Space Science Lab website, ssl.berkeley.edu. There are some opportunities for undergrads, grad students, and I think, for sure, community college students. And I promise you, I had the last slide with an analemma. You can do the Space Science Lab, you get to work with satellites, etc., but you get the best view of the day from campus. So this is one image of the sunset, but we took that image at the same time over the first 5 years, and then the position of the sun at the same time of the day, every day. If you put together all of that, it creates this shape that is called the analemma. And with that, thank you so much. If you want to follow me and contact me, I'm Astronomilo in any social media. Thank you to the organizers. Sorry, I went a little over time.